Okay, so let's discuss fluid stresses. And just like you learned in mechanics of materials, where solids exhibit stresses, there are shear stresses, there are normal stresses. Well, fluids also exhibit shear stresses and normal stresses too. And so, to show that, or to discuss that, and we'll get into a bit more about this later on in class. But let's consider what's called a fluid element. Sometimes a fluid element will be called a fluid parcel or a fluid particle. They're kind of used interchangeably for the purposes of this class. And really what they mean is a very small amount of fluid that basically moves with the flow. And just like with the fake fluid particles for the path lines and streamlines, we're just tagging a small chunk of fluid and basically observing how it moves. And then basically looking at the stresses on that. And so here I'm just going to draw a fluid element. Here we have a little channel, and there could be some water flowing in the channel, and we're going to just draw a fluid element. They don't have to be squares and rectangles. They can be any arbitrary shape. So we have a fluid element. I'll get rid of those. We have a fluid element at some time t0. At some time t0. Okay, and we're just going to observe how this fluid element moves. And at some later time, it can deform, it can move downstream, but the fluid element can change. Okay, and this is the fluid element at time t1. Okay, and it turns out that on each fluid element or fluid particle, there are forces that act inside of the volume and on the surface. And so these are given two appropriate name types of forces that you have on a fluid. There are body forces, and those are forces that occur inside of the fluid particle. So if I get rid of the box over a diagram here I basically zoomed in on a fluid element. Oops. I zoomed in on a fluid element right here. And so here, I just get rid of this to make it more clear. So here's just a fluid element. It looks like a potato. And so there are body forces, and they occur inside. And for our purposes, the only body force that we'll be dealing with in this class is gravity or weight. But some of you who work with advanced propulsion systems or something like that, you may have to deal with magnetic forces, because those also occur within. Magnetic forces and weight occur inside. So weight is occurring due to the mass times gravity that's occurring inside of the control volume. So here, if you were to draw a force for that, you would have weight equals mg, and that equals rho, the density times the volume times g, if rho and g are constant. And you can see how later on in class rho will not be constant, and you'll actually have to do a triple integral to find the mass inside, kind of like what you did with statics, finding centers of masses and things like that. Okay, and the other type of force, well, if there are forces that occur inside and on the surface, and we talked about the forces that occur on the surface and called them body forces, that must mean that the second type of force is called our surface forces. And those are forces that act on the surface. And so the key one that we'll be dealing with a lot in this class is pressure. Pressure is a force that occurs on the surface. And some other surface forces can occur, friction. And friction, believe it or not, there is friction on a fluid element. You could imagine that I have another fake fluid element right here, and this other fluid element is basically rubbing against this first fluid element here. And just like if you had two chunks of solids that were moving past one another, there'd be a friction force, right? And it's the same thing for a fluid. So for a fluid, you still have frictional forces. And what causes the friction, though, is different. It's actually viscosity what causes friction in a fluid. So if you think of honey being thick, a honey is actually not that dense of a fluid, but it has a really high viscosity. And so typically what we think of as a thick fluid is usually a viscous fluid. And these give rise to stresses acting on the surface. So here, if I zoom in to a little patch on the surface, it's going to stick out. It's at some normal direction n hat. I have some differential area delta A, and there's some net force acting on that due to these surface stresses. And if I basically zoom in to that, and it turns out we can resolve this net force into normal components and tangential components. And this is just like you guys did for a solid. Okay? So then the normal stresses, which I'll define with the sigma, sigma n is just delta F in the normal direction divided by delta A. And if you see this equal with 3 signs, that means defined as. Okay, so I think some of you have seen that, some of you may not have seen that. Okay, and this normal stress includes pressure. There's also a viscous stress in the normal direction, but now pressure actually pushes on the surface like that. It does not pull on the surface, it pushes on the surface. And so if I draw a little surface element here, and the outside of the surface is given by n hat, or its direction, and pressure pushes against the surface. And pressure pushes against the surface down. Okay? And so basically that means that pressure is always a compressive stress. You can never have in a fluid you can never have a tensile stress or a tensile pressure. Okay, it is always in compression. And then there are shear stresses, which is normally denoted by tau, and tau is just the limit as the area of this differential patch goes to 0, and you divide the net tangential force. So this acts in the tangential direction, and so that would be the net shear stress. Okay. Okay, and so this is very similar to what you guys did in solid mechanics. Okay, and so here, just to get the nomenclature down, you guys have seen these sort of stress things here. So I have all the stresses. I have a two-dimensional square here. This is the positive x-plane. This here is the negative x-plane. We have the negative y-plane here and the positive y-plane here. And so here on each plane there will be a normal stress that is positive, that is defined to be positive in tension. That is just basic convention. And so you can have a tensile viscous stress in the normal direction, but pressure, again, it always pushes in. And so you have sigma xx, and then you also have shear stresses that are basically trying to rotate the sides of this square here. Okay, and so you have tau xy, tau yx, tau xy going down, and tau yx here. Okay, and then also you can draw the same picture in 3D. It gets a lot more messy, and the fact that I'm not the best drawer in the world really comes to show. But here we have basically we now have 6 faces, because you got to account for the x, y, and the z directions. And so you have sigma xx, which is the normal stress in the y direction, sigma yy, which is the normal stress in the y direction, sigma zz, which is the normal stress in the z direction, and then you have tau xy, shear force on the x face in the y direction, tau xz, a shear force on the positive x face with a force that's acting in the z direction, and so on and so on and so forth. Okay, and so the normal stresses these stresses are given by either sigma or tau to denote whether it's a shear or a normal stress. And notice here that I used a sigma xx or a tau xy. And the first letter indicates what plane that the stress is normal to. Okay, and so basically a tau x or sigma x means that it's a force acting on a plane in the x direction, or that n hat for the plane is pointing in the x direction. Okay, and the second letter here corresponds to the direction of the force produced by that stress. And so sigma xx means that the second x means that the force is acting in the x direction, and this tau xy, this y means that the stress is acting in the positive y direction. Okay, and so you see another example here. So tau yx means that the shear stress is acting on the y plane. So we have a shear stress, and the x means it's pointing in the x direction. So we have a y plane here, and we have a shear stress acting in the positive x direction. So this is tau xy. Okay, and we're going to use this a little bit later on, but not too much. Stresses, you can basically put it into a thing called a tensor. For all intents and purposes for this class, you can think of it as like a matrix, where you basically just fill it with the stress components. So you have sigma xx, sigma yy, sigma zz, and then all the shear stresses right here. Okay, in 3D and in 2D. Okay, and you guys have dealt with that quite a bit in your mechanics of materials. And the normal stress, as I said earlier, it is positive in tension and negative in compression. And shear stress is positive when both the plane and stress direction are positive. Or another way, so if you draw it on this little stress cube here, basically everything is drawn to be in the positive direction. Or in the cubes up here, basically all of them are drawn in their positive directions. Okay, and so you can think of, even though this one is pointing to the left, n hat is pointing to the left. So both the force and the n hat are in the negative direction. And so that would be, and so that still gives a tensile force. And for the shear stresses, you can imagine what these are trying to do is these stresses are actually trying to take this edge here and basically rotate it that way. And if this edge tries to rotate counterclockwise, that gives rise to a positive shear stress. So this portion is just like your solid mechanics. I'm not going to spend too much time on that. So now just to discuss some other differences between solids, just bring up a point that I brought up earlier. And what makes, as I said earlier, what makes a solid different than a fluid is that solids can withstand stress and basically hold their shape, whereas fluids, as long as you keep applying a force, a shearing force, the fluid will keep on moving. So if you think of, if I have a chunk of rubber here, like your eraser, and I apply a shearing force F on the top and bottom of it, and I just let it go for a while. Well, you guys, know from playing with one of those rectangular erasers that you'll basically shear. You'll basically put the eraser into a state of shear, and it will deform, and basically the side will basically rotate by some angle gamma. Okay, and that gamma is actually related to a strain. Okay, and so you've basically induced a shear strain onto this chunk of rubber, which basically means you have rotated it. But if I keep applying the force and time goes on, it basically stays unchanged. That the sort of sheared rubber here, if I keep holding the force, it basically no longer it basically maintains its shape and doesn't change its shape anymore. And so the deformation and stresses are related through G, sigma, tau, K, and tau is equal to the strain modulus times the strain. Now for a fluid, the picture is a bit different, because again, remember, fluids are materials that continuously deform. So if I apply a shearing force to the fluid, just like the solid, it will deform, and it will basically rotate by some angle gamma. And actually for a fluid, I'm going to call it alpha. Okay, but unlike a solid, if I keep applying the force and time keeps going on, what happens is it deforms even more. Okay. So here's a conundrum. I didn't change the force on here, and the angle keeps growing. So this tells us that the shear stress for a fluid cannot equal the total strain that is acting on this little fluid element here. Okay, because basically that means I'm applying the same force, and this angle keeps growing. That is, the total amount of strain keeps growing and growing and growing. But yet you intuitively would not expect the stress because you're applying the same force to keep growing and growing and growing. I mean, that doesn't make any sense. But there is a shear stress acting on this, and one way, as I mentioned earlier, that you can think about this, it's a friction-like effect from basically two fluid elements that are kind of rubbing on one another. So here I have a little picture here, and so here I have a channel, and I have a flow here where in the bottom of the channel the flow is going backwards, and on the top of the channel the flow is going in the positive direction. And I have two fluid elements. I have one right here, and I have a second one right here. And because this upper fluid element is in the top half of the channel, it's moving that way, and this fluid element here is in the lower half of the channel, it's moving to the left. And so you could imagine that these two fluid elements are kind of rubbing against one another, and there's a net friction force. And that net friction force is actually caused by the shear stress right here. Okay. However, like I said, the shear stress cannot be based on the total amount of strain, because that keeps growing and growing and growing and growing, and we know that that if you apply the same force, you intuitively would not get a growing and growing strain. So instead, the shear stress is related to the deformation rate. That is, the shear stress is dependent on how fast this angle is changing. And there's a Newton's law of viscosity, and it turns out that tau is a function of a property of the fluid that's called the dynamic viscosity, or the viscosity, times the strain rate. And so that would be du dy. And to sort of see where that comes from, let's just consider a little fluid element right here that is undergoing a shearing motion. A bit like the rubber band, but I'm just going to take a bit more careful. I'm going to basically mark it up a little bit more. Okay, sorry about that, my iPad would not scroll. So we have our little box here, our fluid element here, and we have a velocity gradient here. So we have the flow here, it basically looks like this. The flow at the bottom here is 0, it's not moving. And the flow at the top here is basically moving at some velocity u, and there's a velocity profile of the fluid across this. So the fluid is not moving here, and up here it is moving at some velocity u. And if I was to plot the velocity as a function of height from the bottom, it would basically look like basically this function here. And so this height here is delta y. Let me fix that. This one looks like a delta x, but it's a delta y. Okay. And there's some net force that I'm basically tugging on the top. And so if I'm to plot the deformation of this little fluid element here carefully, the height is delta y, and if I apply a force, it's going to tug the top over to the right, and it's going to deform the square into a rhombus. Okay, and that's going to change the angle just like the solid. And if we just apply the small angle here, this distance here is going to be some delta L, and the length of the rhombus is not going to change, so that's still going to be delta x, just like it was over here, that the sides are that it's delta x wide and delta y high. Okay, so we can relate, and we know how fast we are pulling the top. We are pulling the top at some velocity delta u, or u for that matter. And so delta L is simply, got rid of the delta here, delta L is simply the velocity times time. So basically this total deformation is related to, or the total amount that it's deformed is related to how fast the top is moving and how long we have moved it. And we're going to use the small angle approximation here. That means that delta L is much, much smaller than delta y. Then that means that the angle here is just delta L divided by delta y, just using the small angle identity for sine. That means that sine theta is approximately theta if theta is small. You guys will use that. If you guys have not used that approximation lots and lots of times, you will, especially in vibrations, when that time comes. Okay? And so the total amount of deformation is delta alpha is equal to delta L divided by delta Y. And I substitute in delta L in terms of the velocity and time. And I simplify. I can divide both sides by this delta t here. And I have delta alpha delta t is equal to delta u over delta y. Well, lo and behold, we can take a limit as delta goes to 0. And if I do that, well, we have a definition of derivative here and another derivative here because we can make the sides of this fluid element very, very small, but still not violating the continuum approximation. And so we have d alpha dt is equal to du dy. And so basically du dy are the velocity gradient, are basically the slope of this velocity function here is related to the deformation rate of the fluid. And so we now know that tau is proportional to the deformation rate, which is proportional to the velocity gradient. Okay, and in reality, tau is more complex in reality, but we're not going to get into that stuff in this class. Okay. Now, aside, we talk about solids and liquids as if there's no in between, but in reality, there are some materials that exhibit characteristics of both. An everyday one that you have experience with, you guys may have eaten some yesterday, is ketchup. Because when it's in the bottle for quite a while, you got the glass Heinz 57 bottle. You need to whack it pretty hard to actually get it to flow. And while it's in that state, it's acting more like a solid than it is a liquid. But after you exceed a critical stress threshold, it starts flowing and it starts behaving like a liquid. Okay. The other one, you may have not heard the name, but the other one is Oobleck. And Oobleck is that famous cornstarch and water mixture that you may have seen the Mythbusters play with. And Oobleck behaves like a liquid in a very low shearing condition. So if you put some in your hand and you just let it sit there, it'll look like it'll kind of melt. And that's because there's no shear force applied to it, and it'll act like a liquid. But under a very high shearing condition, it'll act like a solid. And if you watch the Mythbusters, they can actually run across Oobleck as long as they keep their feet moving. But if they just stand there, they'll sink right in. And so that is another thing. There are gels. Have properties of solids and liquids. That is, they can basically hold their shape if you don't apply a strong force to them. Metals under extreme conditions like high explosive charges, where the pressure can be on the order of gigapascals. Under those conditions, actually solids start to act like a liquid, even though it's not molten. And these types of materials are not a function of this class because they are very complicated. Okay, and now we need to discuss viscosity, which is given by the Greek letter mu. And the units of viscosity are called are in Pascal seconds, in MKS, or poise in CGS. And a poise is just 1 gram per centimeter second. Okay, and this is called mu is called the dynamic or shear viscosity. You will hear both being used quite often. And viscosity is a property of a fluid, so you can think of it as just another property like density and other things like that you might have to get from a table. And it's a function of temperature and sometimes pressure. And for a Newtonian fluid, And for a Newtonian fluid, or what's called a Newtonian fluid, the viscosity just depends on temperature and pressure. If it's non-Newtonian, the viscosity can depend on the strain and on the strain rate, etc. And these are the fluids that start to act like the things that are in between solids and liquids. Blood is a non-Newtonian fluid. Okay, and so now for liquids and gases, the viscosity is a strong function of temperature. For instance, you guys may have seen this in your everyday life. If you put honey in the refrigerator and you try to get it out, it'll flow very, very slowly. But if you put it in the microwave and you heat up honey just a little bit, it starts to become sort of very, very quote unquote thin, and it'll be almost like water. It'll be so thin. So, and the reason it acts thin is because of the dependence of viscosity with temperature. So remember that the shear stress is dependent, or is proportional to the strain rate or the velocity gradient, and which is multiplied by viscosity. And so for a liquid, it turns out that the viscosity decreases substantially with increasing temperature. And this scale here for this plot of the viscosity as a function of temperature, it's on a log scale. So that means that the change of viscosity can be very high for a liquid. But in general, for a liquid, the viscosity decreases as temperature increases. So that means if you heat up a liquid, it will typically become less viscous, and it'll act quote unquote thinner. But again, in this class, do not call a fluid that has low viscosity thin, and a fluid that has high viscosity thick. You can use that in your everyday life, but in this class we need to use a proper scientific nomenclature. And now gases have the opposite behavior. Gases also have viscosity. It's much lower than a liquid. But the viscosity for a gas actually increases with increasing temperature. Okay? And there's a really nice rigorous theory that explains why, and I'm not going to discuss that in this class. But in the back of your book, or any other textbook for that matter, you can find all sorts of information as to how to calculate the viscosity. And the other viscosity that we're going to use quite often is called the kinematic viscosity. And the kinematic viscosity is just simply it's defined to be the dynamic viscosity divided by the fluid density. And it's given by the Greek letter nu. Okay, and so that's the kinematic viscosity. And there are many tables that have both the dynamic viscosity and the kinematic viscosity. And why the kinematic viscosity is used quite often is when you start working with the fluid mechanics, you'll find the grouping mu divided by rho occurring a lot. And so they just basically made a table entry with that thing because it's so common to see it. And nu has units of length squared over time. And so in MKS, it is meters squared per a second, and in CGS, it's centimeters squared per second. Okay, and so now we're going to basically show you how to use this information to calculate forces on plates. So here I'm just going to go through an example. Here where we have a force of 2.5 newtons is required to drag a plate over a thin film of an unknown fluid that is contained by a lower stationary plate. The plate dimensions are 10 centimeters width and 1 centimeter deep. Okay, so in other words, we have two plates, something like this. The bottom one is stationary, and the top one is moving at some velocity. Okay, and we need F equals 2.5 newtons to basically move the top plate. and this bottom plate, as I said, is stationary. And it is 1 centimeter wide. And it is, or deep, I should say. And it is 10 centimeters wide in the x direction. Okay. And if I keep reading the top here, the gap width, that is the distance between the two plates, is 200 micrometers. Okay, and that seems like it's really small, but this could actually be a zoom in of a bearing in your car. And the velocity profile between the plates is linear. That's actually based on an exact theory. That's not an approximation. That's actually realistic. And the velocity is 0 at the bottom plate, and it is 0.5 meters at the top plate. And so what we are asked to do is to find the dynamic viscosity and the kinematic viscosity if the specific gravity of the fluid is 2.11. And note that the top plate is not accelerating. So basically, as I said before, we have two plates, and there is some fluid between those two plates. The velocity between those two plates is linear. So we have, just define a y, we have u of y is linear. Okay, and we're applying a tugging force on the top plate of 2.5 newtons, and it's moving at u equals 0.5 meters per second. Okay, and we basically want to find the viscosity. Okay, so here I just have this drawn again, and this is oil. We have 2.5 meters per second here, no velocity here. We know that the profile, that the velocity as a function of y, and again y is up from the bottom plate, is linear. The height between the two plates is, oops, wrong one. The height between the two plates is 200 micrometers. It's 10 centimeters wide and 1 centimeter deep. Okay, and we are asked to find the viscosities. And so for this type of problem, we need to write assumptions, and in your guys' homework, I expect you to write all of the assumptions that you're going to use. So you're assuming constant properties. And what that means is that, well, you know, maybe the temperature is higher on the top plate than it is on the bottom plate, which means the viscosity will be higher here than it is down here. Well, we're going to assume that the viscosity is not a function of position, that it is constant in the fluid, which you could think of as oil, that is between the top plate. And also the density is also constant. Okay, and we're going to assume that the fluid velocity is not a function of x or z. Okay, and so basically the fluid velocity is only a function of height above the bottom plate. Okay, and we're going to assume that no slip holds. And the no slip condition is the condition where fluids basically sticks to a solid surface, and I'll discuss more about that later on. Okay. And so the solution, where do we begin? So for the solution, we want to first just take note of what we know. We know that we have a plate on the top, and we're applying some force to that plate. Okay, because the plate is moving basically this way. Okay, and so we know that it's not accelerating, and so that means that sum of F in the x direction equals 0 on the top plate. And so that means there needs to be some force here acting opposite to our applied force that is resisting that motion. Well, that force is actually friction from the fluid. So I'll call that F shear. Okay. So how do we find F shear? Well, first are the friction force from the fluid. So first, let's just define a little patch called of size dA, and it's of height dz, and it's of width dx. Okay, so it is dx wide and dz deep. Okay, and then there is a differential. There is a differential shear force acting on that. So, and then the net shear force is just equal to the sum of all the differential shear forces on all these little dAs. And so that is just the integral over the plate area times the differential shear forces. Okay, so now to complete this integral, we need to find the net shear forces. Okay, well, we know that, and I'll just call this dF to save some writing. dF. Because we're just understanding that it's a shear force. So dF equals, well, we have a shear stress, so that's tau xy, so that's a shear force acting on the y face. Oops, wrong one. Acting on the y face in the x direction. Okay, times dA, right? Because force is just stress times area. Well, our dA is dx dz. So dF is just tau xy dx dz. Well, how do we find the shear force? Well, we know from the above discussion that shear force is just the viscosity times the velocity gradient. Okay. So now how do we find the velocity gradient? How do we do that? Well, let's just take note of what the instructions said. We have a top plate over here, and that's moving at 0.5 meters per second. And we have a bottom plate where the fluid velocity is equal to 0. Okay, and we are told that the velocity profile is linear. So the velocity profile looks something like this. So we have u equals 0.5 meters per second here, and u equals 0 meters per second down here, and there's a straight line connecting those. And so you could just say, we call this height h, and I'm just going to call this u top. Again, in this class, I'm going to try to get you guys into the habit of working symbolically all the way up to the end, so you can get a nice little formula that you can just plug in your numbers. Okay, so we know that u at the top of the plate is equal to u top, and u on the bottom, which is at y equals to 0, equals 0. So we basically have, we know that there's a straight line, and we know 2 points on that line. And so you can just basically use u equals my plus b. Just use the formula for a linear line and solve for m and b. And in your homework, I would expect you to show that. But we find that u of y, which is a function of y, equals the velocity at the top times y divided by the gap width between the two plates. Okay? So then, we also know du dy, because we can just take the derivative, and that equals du top, du top, y over h dy, and that's just equal to u top over h. Okay, because again, we're assuming that the plate itself is not deforming, and that means that basically this little chunk of the plate is moving at the same velocity as this chunk of the plate back there. It'd be a really complicated problem if the plate was tearing into two pieces, but we're not going to do that. I'm not that mean. Okay, and so now we know just basically we know what the velocity is, and so the shear stress then is equal to mu times u top over the plate height. Okay, so then our differential shear force dF equals mu times the velocity of the top plate divided by h times the differential area, which is dx dz. So now we know, in terms of all of our knowns, we know the total force acting on that little plate area. So now, for the purposes of getting a nice formula, I'm going to call this distance here W, and this distance here L. Okay? And so now, we need to integrate all of these shear forces and basically all of these tiny little dAs over the entire plate. Okay? So then F equals the integral over the plate area times dF. That equals the integral from 0 to L times the integral of 0 to W of the differential force. That's mu times u top over h dz dx, I should say. Okay, and so basically we're just integrating over a plate, and that winds up being a double integral. But fortunately, these here are just constants, so we can pull those out because we're assuming constant properties. And we're also assuming that the top plate the top plate and H are also not changing. And so this equals, then this implies that F equals mu times the velocity of the top plate divided by H times the double integral of 0 to L and of 0 to W dz dx. Well, this is a pretty simple integral. Here, this implies that F equals mu times u top over h times L W. Okay, and now the problem, we know, for the problem statement, we know F, we know u top, we know h, we know L, we know W, and we want to find mu. So then mu is equal to F, the applied force on the top plate, divided by the top plate velocity times h over L W. Okay, and so we have our nice little formula. And in your guys' homework, I expect you guys to basically do this. Is basically don't stick in numbers until the very end. there's only a few problems in this class where it becomes to where it's not conducive to do that. Okay, and so now we're going to stick in our numbers. So mu, or the dynamic viscosity, is equal to F, which is 2.5 newtons, divided by the top plate velocity, 0.5 meters per second, times the gap width, which is 200 micrometers, divided by the plate width, length, and the width is 0.1 meters, times 0.01 meters. It's just 10 centimeters. It's just 10 centimeters and 1 centimeter. Simple conversions like that you can do. But again, always show if there is a number, then there is a unit attached to that number. And then we're gonna convert micrometers to meters. So we have 1 meter per 10 to the 6 micrometers. So you punch in the numbers into your calculator, and you find that mu equals 1 Newton second per meter squared. Okay, and now for the kinematic viscosity, nu equals mu over rho. Well, remember that we're not given rho, we're given the specific gravity. So that equals mu over rho of water times the specific gravity of the fluid. Well, the density of water is just 1,000 kilograms per cubic meter. And now we know all the numbers, so we basically stick them in. So we have 1 Newton a second per meter squared, or Pascal second, divided by 1,000 kilograms per meter cubed times the specific gravity times 2.11, and that's unitless, so we don't need to. So there are no units attached to that. And now let's start converting the newtons up here to kilograms meters per second squared. So we have a Newton is equal to kilogram meter per second squared. And so now all the units cancel out, the newtons cancel out, the kilograms cancel out, and this meter squared cancel out. These cancel out, and one of these seconds cancel out. And so what we are left with is that the kinematic viscosity, if you punch in the numbers in your calculator, is 4.74 times 10 to the minus 4 meters squared per second. Okay, and so that's how we solve that problem. And so last topic, and that will be surface tension. Surface tension is a force that is developed at the interface between solids and gases between two or more immiscible fluids. And that could be, for example, oil and water, or water and air. And the cause of surface tension, it's actually a surface stress, or it's a stress, is this is what produces liquids to behave as if they have a quote-unquote skin, even though there really isn't a skin. It's not a real scientific thing. And surface tension is what causes droplets and things like that to have a roughly spherical shape. It's what causes bubbles to basically look like little spheres. It's what causes raindrops to look like what they are. And well, that's in combination with aerodynamic forces, things like that. And it's caused by an imbalance of forces at the surface of a liquid at the molecular level. So here, if we zoom in to a surface at the molecular level, we have a bunch of little liquid molecules, and the surface of them is right here. And for a liquid, there are all these attractive forces that basically all of these little molecules are basically attracting one another. And the ones in the middle are free because there's no net force on them, because they are equally being tugged in this direction as they are in this direction, as they are in this direction, as they are in this direction. But for the molecules on the surface, it's a different story. There's a net tugging down. There is very little tugging of them up. Okay, and so because of that, on the very top surface, there is a net force that is acting down, basically due to that. Okay, so I'll just finish this, and so these net attractive forces that are on the surface are actually what cause surface tension, and also the same picture also applies to solids. And solids actually have a very, 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 very small surface tension. But there is a surface tension. It's just its effect, you don't even need to consider it in any realistic calculation for anything that you would pretty much ever do. And also, what causes it to have more of an influence on fluids is the fact that for a solid can withstand that stress without deforming, or deforming on the order of, a couple nanometers or something like that, if that. But for a liquid, it will basically, the imbalance in surface tension will cause the fluid to deform until it maintains some sort of equilibrium shape, and that is normally a sphere. Okay, and the surface tension depends on the fluid, the temperature, and the fluid, and the material that the fluid is in contact with. So that is the surface tension. There's no such thing as a surface tension of water. So no such thing as surface tension of water. Okay, surface tension is a function of the interface. Is a function of the interface. Okay, so that basically means is that the surface tension depends on both materials, that is, the air and the water. Okay, and so surface tension basically causes a tensile force acting on the surface, and the total force and the surface tension is denoted by sigma. That's not to be confused with normal stress in the stress tensor. And the magnitude of that force is the surface tension times a contact line on that surface, and I'll draw what that means in a few minutes. Okay, but remember, the sigma here is the surface tension, and it's a property of the interface. And so the sigma is different for a water droplet in oil, like in your salad dressing or something like that, or a water droplet in air. Even though the main liquid that we are worried about in both cases is water, the surface tension has two different values, because again, it's a function of the interface. And in your salad dressing, it's an interface between water and oil. And for a rain droplet, it is the interface between water and air. Okay, and so you can't just look up surface tension for water. You need to look at what interface it is. Okay, and so if we look at and surface tension actually causes a pressure rise in droplets and bubbles. That is, the pressure inside the droplet will be a little bit higher than the pressure outside, or Or same thing for a bubble. Okay, so if we consider a bubble here, we have liquid outside, and this here is our bubble. And we're assuming it's a perfect sphere, even though I've not drawn it to be so. And so we have some pressure acting outside of it, and there's some surface tension that we can define on this interface. And the radius of the bubble is r, and we want to find some net pressure inside. Okay, so how do we find that net pressure inside? Well, first, the total surface tension force is given by the surface tension times the contact line, and that's the contact between, and that's the interface. And I'll basically show you what that means in the next diagram. So here, we're just going to take this surface, and I'm going to make an arbitrary cut right here along the not the equator, but whatever the thing 90 degrees is, that is 90 degrees to the equator. I'm going to draw a free body diagram because we know this bubble is not accelerating, it's not changing shape, and so it's going to be in static equilibrium. So let's draw the free body diagram. Oops. Oh, and I forgot, sorry about that. And surface tension has units of force per unit length, or in MKS, newtons per meter. Okay, and so we have our free body diagram here. We have half of the bubble here, like this, and so we have pressure pushing outside of the droplet. That will be pushing it, trying to push it to the left. We have pressure inside of the droplet. That's basically pushing on our little planar surface here. That looks like this. And we have surface tension, and surface tension acts on the interface between the air, between the air inside the bubble and the liquid outside. And so this contact line is actually this basically line that is on the circumference. Okay, and so there's a net surface tension force, and that is a net tensile force. It's not compressing it; it's actually trying to pull the surface together. Okay, and so we're in static equilibrium. So we have sum of Fx is equal to 0. Well, we have pressure forces here acting inside the droplet that are trying to push everything to the right. And so that's just Pn times area minus the surface tension forces which are trying to pull it together. And so that's equal to the surface tension property of the interface times the contact length minus the external pressure times A. And in the next chapter we will prove that that is correct. And that's equal to 0. Well, this implies that Pn minus P out is equal to the surface tension times the length divided by the area. Well, the area here is just the area of this circle, and that's pi r squared, and this contact line is just the circumference, because again it's the line along which it's the line along the interface, and that's 2 pi r. And so, and this pressure difference is the difference between the pressure inside of the bubble and outside of it, and I'm just going to call that delta P. So this implies that delta P equals 2 times sigma over R. Okay, and that's for a spherical bubble or droplet. Okay, and so that means inside of a bubble or a droplet, the surface tension is always a positive number, and the radius is a positive number. that means that the pressure inside of a bubble or droplet is always higher. Okay, and so that's just how that is. Okay, and that net pressure force, because the pressure is higher, it's being balanced by this extra surface tension force that is trying to hold the droplet together, or the bubble together. Okay, in general, you can generalize this formula here. This here, 2 over r, is just the curvature of a sphere. And so this equals kappa, which is the curvature, times the surface tension coefficient. And this is curvature. Okay, and this is the general formula that you would use. Okay. And the other thing that surface tension causes is surface tension, or sigma, can also cause fluids to rise or fall in small tubes. That is, it can cause capillary forces. Okay, and so if we consider some water here and a very small tube, a surface tension will often cause that water to rise up. Okay, and will often cause that water to rise up. And essentially what causes that is that the surface of the water in the tube has this sort of curve. And remember, the surface tension is acting in the direction normal to the surface. So the surface tension force acts in the direction of the surface. And so here the surface is at some angle, theta. Here, and they actually measure that angle. It's called a contact angle. And so again, we do a free body diagram of this fluid element right here, because we know the water's not falling down, it's not rising up, and it's not accelerating in any way. And just remember, this triangle with the 3 lines, that means atmospheric pressure. And this whole little slug of water here is going to rise up some height, small h. Okay, and so we just draw, we're going to assume static equilibrium. So we're going to do a free body diagram to analyze for a given surface tension, coefficient, and angle, how high does the water rise in the tube. Okay, and so we have atmospheric pressure that is pushing down from the top. We have some atmospheric pressure pushing up from the bottom, and this will make sense when we do fluid statics here in the next chapter. And for the purposes to make the analysis easier, we're going to neglect the volume in this meniscus. But these pressure forces acting up and down are balanced by the weight of the water in this little in this little piece that is lifted higher, and also the surface tension which acts in the direction of the surface. Okay, and so we have a surface tension acting in this direction, and that's given by sigma times L. Okay, and this is a circular tube of radius r. Okay, and so we just apply static equilibrium again. And that's equal to 0 because it's not accelerating. That equals 0 times minus P naught, which is the outside pressure, times A. That's trying to push the top of the water down. Minus the weight, which is mass times gravity, plus the surface tension times the length times cosine theta, right? Because we are summing the forces in the y direction. Oops. We are summing the forces in the y direction, and that is that component there. And so that is sigma times the length times cosine of theta plus the pressure acting on the bottom, pushing up, and that's P naught times the area. Well, these cancel out, and we know that mass is equal to rho times the volume. That equals rho times pi r squared h. Because again, it's a circular tube, and so it's just pi r squared times the height. And again, we are neglecting the tiny volume due to the meniscus. It's normally very small compared to everything else. Plus the surface tension times the length times cosine theta, which is a given, or which is normally a given, and L is equal to 2 pi r again, because again this is a circular tube. Okay, so then this implies that minus rho times pi r squared hg plus sigma times 2 pi r cosine theta is equal to 0. This implies that h equals 2 sigma cosine theta over rho g r. Okay, and this here is just gamma, and that's the specific weight. Okay, and so this implies that in a little tube, that the height that the water will rise up, or the height that a liquid will rise up, is h is equal to 2 times sigma cosine theta over the specific weight times r, or if you know the density, 2 times the surface tension of that interface times cosine theta over rho times g r. Both of those equations are equivalent. Okay, and there's another example that I will post another video on, an extra video on. This video is getting pretty long to begin with.